So we mentioned last time that we could obtain eigenfunctions of the Koopman operator from data. It's time to approach that problem in a systematic way. So we are going to talk about numerical methods. So we have introduced the notions of spectral expansions, the eigenvalues of the Koopman operator, the eigenfunctions, the Koopman modes, and the issue in this lecture and a few coming lectures is going to be how do we exactly go about computing these, provided we have access only to data. And the key idea is that we truly want to compute things from data, not from a state space model. So we want to be truly data driven in the sense that there is no underlying model, but we would still like to find out what the eigenvalues, eigenfunctions of the operator are. And then if we find that out, we can go back to the state space, because we know that if we compute eigenfunctions, then the level sets of eigenfunctions give us the geometry of the state space. So that's going to be the topic. The topic itself is going to be computing eigenfunctions, eigenvalues, modes directly from measurements. And one of the most interesting problems in data analysis is the situation in which we don't have many distributed sensors. So maybe we have access to only one function and one function evolving over time. And it's kind of an interesting question to ask, what can be achieved in that particular situation. And interestingly, with the help of the Koopman operator theory, we will learn that, in fact, quite a bit can be achieved. The most common way of computing eigenvalues and eigenfunctions is via a representation of the operator. I spoke in the last lecture, which was on Karleman linearization, on how one can represent the operator in terms of a matrix. And in that case, we used monomials as quote unquote basis. On finite intervals, for example, on the real line, monomials in fact do form a basis, but they're not a basis on the whole real line because of some technical issues with that particular set of functions. But the key idea was there, in the sense that we evaluated the action of the operator on the set of basis functions, and then we produced a matrix that represented the operator in that particular basis. So those kinds of approaches in numerical analysis are called Galerkin projections, and we'll speak about them. And clearly, the Koopman operator is commonly an infinite dimensional operator, except if we are working on a discrete space. And therefore, we are going to need to discuss truncations of the representation of the operator with some finite number of basis elements. There is another problem that we are going to face, and that is, suppose that you have a nice basis on, let's say, interval 0, 1. We might use the basis of harmonic functions, sines and cosines. And then suppose we have then a situation where we introduce another dimension. So we have really a two-dimensional system, and we have the square 0, 1, 0, 1, on which the evolution of our system is happening. And so we have sines and cosines on this interval, and then we have sines and cosines on this interval in y, right, and x. And so we could possibly form the basis out of sine 2 pi x times j and then cosine of 2 pi x times j, sine 2 pi y, k. And we would find out very soon that those individual functions cannot form a basis, but we would need to do something like form products like this. So sine times cosine, and let's say this cosine is, the argument is 2 pi y k. So for integers k and j, this would give us a countable set of basis functions. In fact, give us a basis. But let's say we truncate and we take 10 sines and 10 cosines. Well, the multiplication of those 10 functions in x and 10 functions in y is going to give us 100 functions. So now suppose we go to 3 dimensions, that's going to give us 1,000 functions. 4 dimensions, 10,000, and as you can see, there is an exponential explosion in the number of elements in the basis, and that certainly presents a problem. It's the so-called curse of dimensionality. So we're going to need to deal with those kinds of issues, and we'll see that something is called Krylov subspace methods provide us with a way of avoiding exponential proliferation of these basis elements. But at the same time, these are interesting because we can use them starting from a single observable. And it's a beautiful fact that even if you take a single observable and you compose it with a mapping, you obtain a new function. And so the dynamics itself generates new quote unquote basis functions. And that's something that we are going to explore because it's essentially a sampling in function space. And that's an interesting concept. Now, prior to doing these kinds of methods that in fact use functions to represent the operator, we'll introduce something that's called the generalized Laplace analysis. And generalized Laplace analysis is a rigorous method. It in fact gives us ability to obtain eigenfunctions and eigenvalues and modes without constructing the operator. This is quite nice as a property. To explain it intuitively, let's suppose that one has just a matrix A acting on some space, finite dimensional space. And then we choose a vector V and construct the sequence AV, A squared V, and then we continue this sequence A to the n V. So starting from some initial vector V, we construct this sequence. As n goes to infinity, and in general, if the top eigenvalue, the largest eigenvalue of A is has a norm different from 1, this sequence is going to end up aligning with the top eigenvector, right? Which is the statement that this linear dynamical system, for example, is going to be such that the iterates of the matrix of the trajectory are going to lead to alignment with the top eigenvector direction, right? So the point is that we never need to know A in order to find out this eigenvector with some normalization, because this might blow up, but with some normalization that might go to the eigenvector, let's call it V star of this matrix. The point is that the only thing that we need to know is really how A acts on V. So we could just observe the sequence of vectors and normalize it so that it doesn't blow up to infinity, and we would obtain an eigenvector. So Generalized Laplace analysis is an idea that's very similar to that, but we are going to remove these requirements that the magnitude of the eigenvalue has to be different from 1. And so that's kind of the tricky part, but also at the same time, maybe, is some of the earliest work in this direction onto how to obtain eigenfunctions from data. So we'll start with this notion of generalized Laplace analysis, and then we are going to go to Galerkin projection for effective reasons that generalized Laplace analysis doesn't really have a curse of dimensionality associated with it, and it doesn't require us to exhibit the operator itself. So we can get it directly from data. And we have seen elements of this before. So, for example, we discussed the computation of the eigenspace at 0, invariance, really, the basis of attraction for fixed point systems using time averages. So the way we did this is we said, okay, let's start from some initial condition x, and then generate this h star, the time average. The time average was obtained by taking samples of h, namely taking values of h along a trajectory starting from x. So s as usual, st as usual is the flow associated with our dynamical system. X dot is f of x. Then we take the limit when t goes to infinity, 1 over t, integral from 0 to t of those values along the trajectory. And what we proved is that for fixed point attractors, the Koopman operator acts on that h star by as an identity, essentially. So ut h star of x is h star of x, meaning that h star of x is an eigenfunction of ut, so of this family of operators for any t with eigenvalue e to the 0t, or in other words, 1. So 0 is the eigenvalue in the continuous time case, but we have to remember that we exponentiate. So we have e to the 0, e to the 0 times t there. All right. Now, we didn't prove this yet, but this kind of a statement, so taking time averages, it's valid in a much larger context. So it's not only valid for fixed point attractors, it is also valid if we have limit cycle attractors, toroidal, not toroidal, toroidal attractors. It's a D here. And Milnor attractors. We'll discuss those concepts a little bit later. And so let's see how that generalizes. So the way we are going to generalize it is introducing the idea that we can take the same samples along a trajectory, but now we're going to put a weight, some function a of tau. Tau represents this variable inside the integral, so a dummy variable that is really the time along the trajectory. And so so we get h star of x is limit when t goes to infinity, 1 over t, integral from 0 to t, a of tau, which in the case of time averages would be just 1, h of s tau x d tau. And if we want to approximate that integral, well, that's easy. Let's take delta tau to be the sampling interval, j the counter variable, so j is going to go from 0 to nj, and we're going to divide by nj here. So we're going to divide by nj, by the total number of steps we've taken. And then we are going to take samples along the trajectory, h of s at times j delta tau x. So we had this time series here. And if we have the weights, we can certainly construct this approximation, and that approximation is going to hopefully get better and better as nj goes to infinity. Now, For that, we would of course have to take a, in many cases, a sufficiently small delta tau, or put some requirements on delta tau, but we will not discuss the details of that at this point. So let's now see what kind of form we can put this in. So let's now obtain a vectorized set of initial conditions xk. So let's take some initial conditions in some subdomain in some subdomain of state space that we're interested in. So we have a bunch of initial conditions. So we could position them in a lattice like this, and so that would be x1 to x and k, and we're going to vectorize that. So we're going to put x1 to x and k into a matrix, and we're also going to vectorize the weights. Aj, we're going to write it as A of j delta tau. So this is sampled weights. And then we're going to write H star A. So this H star here, which is going to represent an approximation of an eigenfunction, in fact, depends on the set of weights. So this H here that you see depends on the time sampling and the space sampling, is called a data matrix. The typical data matrix and object that we're going to have in the Galerkin projection a little bit later when we want to exhibit the operator. But while this term here, h of s tau x, is indeed u tau h of x, so you could say, well, there is an operator here. You really don't need to know u tau itself. That's an operator that acts on all the functions on the state space. You really need to know how it evolves forward h itself. So what is prominent in this formula is just the samples of the function. There is no operator involved in this particular approximation. So now we have these initial conditions, and we have sampling time of our weights, and we're going to call H star A the product of the matrix H and our weights A. So as I said, H is a data matrix. In its rows, you have H starting from the same X at different times. In its columns, it's H at different initial conditions. So let's take A of t to be just 1. So that is e to the 0 times t, as I said before. So that means that our eigenvalue is the eigenfunction that we are interested in is associated with eigenvalue 0. We get H star A is the data matrix multiplying 1. And this 1 is a vector of 1s with nj components. Right? So now, if we get the data matrix H, we multiply it with this vector of weights, and automatically we obtain an approximation of the eigenfunction, because this H star A is just a vector of time averages. Well, in this case, when we have weights 1, there will be a vector of time averages starting from different initial conditions. And therefore, on the state space, it's an approximation of, in this case, the time average along a trajectory, and therefore an eigenfunction. So here we would have some kind of a discretized set of values that would correspond to an eigenfunction, again, assuming convergence that we have proved, at least for the fixed point attractors, but as I said, it's valid in a much larger context. So let's now, so this is the basic intuition. Let's now discuss a more general context. So we're going to take a function f that is really what we call a bounded field of observables. So that f is going to depend both on the initial conditions, the states, but it's also going to depend on an indexing set A. So the idea here is that we might have, let's say, the evolution of a temperature. That's our observable. On a line, so this is going to be the z direction. And this is going to be x1, and this is going to be x2. And so starting from some initial condition x1, x2, at any given time t, we are going to have an associated profile of the temperature along this interval here. So in that case, we would have t that depends on x. This is really the initial condition that I'm going to talk about in a second, and then z is really a point on the line on the interval. Let's say we have a rod that looks something like this, and it's attached to the wall, and there is some temperature T0 here, and we start at time T is equal to 0 with a certain temperature profile here. It could be just a uniform temperature, right? And then over time, you know, the temperature here, if T0 is bigger than this uniform temperature, so over time, the temperature is going to rise, right? And we are going to have those different curves. So the observations at different points z of the temperature at a different time will give us the evolution forward of this field here. And observing that, we'd like to find the eigenfunctions and the modes of the associated evolution. That's the idea. So you know, if we can drop the dependence on the state space variable on the initial condition, we're just considering evolution from a single initial condition, then we write this field as f of z. And then u is going to be the Koopman operator associated with the map T. We have discretized our evolution as tau, right? We have discretized it to certain discrete intervals, and so the associated operator would be u delta tau. This associated operator is u delta tau, but I dropped delta tau from the notation here, and instead of st, we have a map that takes us from j times delta tau to j plus 1 times delta tau. So one step in time. Now some mathematical conditions. We're going to assume that the operator u is bounded and that it's acting on a vector space of continuous functions. And by the way, this does not have to be the space of all continuous functions on M. The reason being that very often in observations we have access only to a finite resolution, and so that's actually going to physically restrict the space of functions. For example, we could not measure, or in every case of measurement, we cannot measure oscillations faster than a certain predefined resolution frequency. All right, so now that we have the setup, we can talk a little bit about the main theorem that tells us something about how we can compute eigenfunctions and modes, as I said, without exhibiting the operator. So we're going to assume this setting. We're going to consider lambda 0 to lambda k to be simple eigenvalues. So we're going to ask for no repeat eigenvalues. And we're going to request that 1 is bigger than equal the norm of lambda 0, bigger than equal norm than lambda 1, so on, and then lambda k is bigger than 0. So this is really an assumption that says that we are restricting our attention to eigenvalues in the complex plane that are inside the unit circle, something like this. So we could have eigenvalue 1. We could have some other eigenvalues on the unit circle. Remember, we are discretizing our problem, so we're operating in discrete time. So we might have this kind of a distribution, of eigenvalues. So this would be this lambda 0 is equal to 1, and lambda 1 and lambda 2 would be these complex conjugates here, lambda 3 over here, lambda 4 and lambda 5 is again complex, and then lambda 6. Okay, in this particular case would be the 6. But this is the typical picture. And so what we're really doing here is we are restricting our attention to a kind of finite frequency space. The eigenvalues that go towards here are faster, and the eigenvalues that go towards here are slower. One is in particular omega is equal to 0, the infinite period or the time average, so the slowest period. And then these other ones have kind of a dissipation rate that is progressively larger in the sense that, but still, not kind of infinite, which is something that we would get with lambda k is equal to 0. All right, we are also requiring there are no other points in the spectrum of U with lambda bigger than lambda k. Those are the requirements, and they essentially reduce to saying, well, we're considering a finite resolution system. Maybe we're looking at an infinite dimensional system, but we have finite resolution of our measurements. We can only get a finite number of eigenvalues out of those. So that's the situation we're going to take a look at. And then the theorem says that the Koopman mode associated with lambda k is obtained by computing the following sum. So I'll say one more thing before I go to this expression. For a linear system that is, for example, stable, this would obviously be true if we restricted our space of observables to linear functions. Those are the theorems that we proved in the section on linear systems. So how do we obtain this quantity fk, which is in fact, a multiple of the Koopman mode? So what we do is we start with lambda 0 really, and in that case we don't have this term, and we compute this weighted sum. This is f, the chosen observables that we have, sampled along a trajectory of ti at some physical point, let's indexing point z. So if you want, what I'm going to do in a second is I'm going to remove this z from consideration But if you actually look at this with lambda k to minus I, that should look very similar to the sum over here. And so A of j delta tau would be literally the lambda to power minus j. That would be the weight. But the idea is that Koopman modes and eigenfunctions are computed as weighted averages along trajectories. And I'll point out in a moment as to why this part here is necessary to proceed doing that. Namely, if all the lambda k's that we have, all the eigenvalues that we had, were of magnitude 1, then we wouldn't need to remove this. This removal happens because of the fact that if you want to obtain the mode that corresponds to this eigenvalue over here, then if you multiply with lambda, with this lambda, with 1, 2, 3, 4, that's lambda 4, to power minus I, since lambda 4 has magnitude less than 1, this term here is going to explode. Let's suppose that you multiply it just with, a constant value that is corresponding to eigenvalue 1, then you get infinity from this sum, because this is exponentially growing and this is linearly growing with n, right? So the idea is that one needs to remove all the components of the signal that correspond to eigenvalues that have larger magnitude in order to compute on a reduced space in which we can control the growth of this using the decay of this part. So again, to repeat, our eigenvalues are between 1 and 0. This would grow exponentially in that case for anything that has magnitude less than 1. So this is going to then, the only chance to get a finite result is that this decays exponentially, and this subtraction is exactly there to ensure that. So while it looks complicated, it's not intuitively very complicated. We basically take the signal f, we subtract the modes that are corresponding to larger magnitude, and then we compute on this reduced signal to obtain the modes. Now I should say the fk here is really the Koopman mode sk multiplied by some value that depends on the initial condition. So it's really a weighted Koopman mode. Phi k itself is an eigenfunction of u, and the norm of that phi k is chosen to be 1, and sk is the kth, what we call the kth Koopman mode, given that choice. All right, so I'll give a brief outline of the proof. So the key idea is to start with the 0th eigenvalue. That's the first one, the largest magnitude, and introduce a new operator u lambda 0, which we obtain by taking the Koopman operator and multiplying by lambda 0 to inverse. And now we can use a similar calculation to what we've seen before. We apply u to the limit when n goes to infinity, 1 over n, sum I 0 to n minus 1, u to power I lambda 0. Remember, that's this u lambda 0. So when we put it in power I, we get lambda 0 to minus I here. So lambda 0, in this case, k is equal to 0, lambda 0 to minus I. We don't have any of this part over here yet because we are working with the largest eigenvalue. Okay, u passes to the inside by linearity, and we get limit when n goes to infinity, 1 over n, sum I is equal 0 to n minus 1, lambda 0 to minus I ui g of tx. This is just the composition, right? So it's just by definition of u. By definition, this function here, when acted upon with u, gives us the composition of the function with t, and that's what is in there. But what that provides is another, of course, another power on the Koopman on the Koopman operator. So we get I plus 1 acting on g over here. And so what happens then is we take limit when n goes to infinity, we can pull lambda 0 out, and what we get then on the inside is I plus 1 multiply, exponent to lambda 0, and I plus 1 exponent to u. That's nice because this looks very much like the original sum, except that, of course, I starts with 0, right, here. But here we start the sum with 1. And then here we go to n minus 1. But of course, this sum goes to n because it's I plus 1. So we need to subtract a term, in particular g of x. And then we need to add a term, lambda 0 to minus n g to tn x, in order to balance if we want to produce a sum that is exactly the same as this one. So starting from 0 to n minus 1, we have to subtract g of x because we have added g of x to this to produce this, and then add this last term. So that's the idea. Subtract g of x, add this last term, which is lambda 0 to minus n g to tn x. And then we obtain the first term that is pretty much, when you take the limit, exactly the same as this. Limit when n goes to infinity, 1 over n multiplying multiplying g. G is finite, so this is gonna vanish. So that's gone. And then here is the last term. You have to worry about that one a little bit because lambda 0 is less than 1. And that's going to exponentially explode. This is finite though. This is finite though. And it contains this t to the nx. And I'm not going to dwell on this last part too much, but there is a way of obtaining an estimate of this that exactly cancels lambda 0 to minus n and provide us with a finite value. And so that last line actually vanishes when n goes to infinity as well. And so we get lambda 0 times this first term, which is the same as this. And so we really get u, we are calling this weighted sum g star lambda 0. So g star is just like the time average, but lambda 0 itself is denoting the fact, indicating the fact that we're using an eigenvalue or weight that is different than 1 here. And what we obtained by the theorem is u g star lambda 0 is lambda 0 g star lambda 0. Okay. So u g star lambda 0 is, when this term is gone, just lambda 0 g star lambda 0. And that's really the crux of the whole calculation. This proves, under the conditions that I've stated, that g star lambda 0 of x is an eigenfunction of u at eigenvalue lambda 0. All right, so now we obtained this G star lambda 0 of X. We didn't really work with the field of observables, but that's relatively simple because, you know, this whole field of observables is actually parameterized by Z. So if you took F star lambda 0 of X parameterized by the Z, for every Z, you would get an eigenfunction that depends on X multiplied by some value that depends by Z. And so that value as a function of Z is the Koopman mode itself, right? That's what we call a Koopman mode. It's basically taking F and projecting it, so this field F, and projecting it onto the eigenfunction phi k. So Sj of Z is the mode, itself. And I'll summarize this projection idea by saying that P lambda 0, which is just this scaled operator U lambda 0 I, summed, divided by n, limit taken and n goes to infinity, then that's actually a projection operator. So if you apply it twice, you get back the operator itself. So the space of functions that we started with, this space of continuous functions, we can split into a possibly non-orthogonal direct sum, which is the set of all functions that this projects onto, plus whatever else. So that's identity minus P lambda 0 C. And so now what happens in terms of this picture here is, let's say we projected onto this eigenvalue or eigenfunction corresponding to eigenvalue 0. And now we're going to continue and project, let's say, on these two. So we're just going to subtract whatever we had and obtain really a new signal. That's the idea. We'll obtain a new signal. So really, to start with, we're gonna say something like, okay, I had the signal F. Now I'm going to subtract F star lambda 0. And then if lambda 0 is different than 1, I'm going to have to subtract its evolution in time. So this is going to be lambda 0, let's say j, where j goes from 0 to infinity. And this is going to be the jth sample of the signal. And this is the new signal that I'm going to be working on. And that's really what this particular subtraction means, except that I started, now I'm assuming already I did this for k eigenvalues, and I now want to proceed. I did it for k eigenvalues, and now I want to proceed to k plus 1. So we subtract elements of the signal that corresponds to evolution using eigenvalues lambda. And now we, in essence, have a reduced space of observables on which the operator itself has a smaller set of eigenvalues. So when we come to the last eigenvalue over here, we will have already subtracted all the parts that correspond to the other eigenspaces. And so the operator restricted to this eigenspace is going to have one eigenvalue. That's kind of the key idea, right? Okay. So to get back to the statement after going through the proof, the statement said basically what I indicated in this last discussion, and that is Fi that depend on this indexing set Z, that could be a physical point. That's the signal that you're obtaining. Let's say you have a temperature at a particular point in the field, right? So you have a bar, and at this point here, you're measuring the temperature over time. So your F is really the temperature T. And then the samples are Ti. So I counts the number of intervals we have taken in sampling this. We subtract from that the previous, the weighted sums that correspond to eigenvalues that we already dealt with. So those would be the lambda j from 0 to k minus 1. So if we wanted to find the kth mode, kth eigenfunction, we would construct these sums, subtract that from the signal, multiply by lambda k2 minus 1, divide by n, and take the limit, or rather cut off at some finite n to produce the result. Now, in order to do that, of course, we somehow have to have an idea of what the eigenvalues are. And so that has to be done independently in order to produce a result of this sort. So that has to be done separately from this calculation, and somehow you need to have an estimate of the eigenvalue to start with. Okay, so some remarks. The Fj that we found, that is a product of the Koopman eigenfunction and the mode, is what is called a skew projection of the field of observables on the eigenspace of the Koopman operator associated with eigenvalue lambda j. You could ask a question. Well, what if I have something like a rotation on a unit circle, and my eigenvalues on the unit circle actually densely cover the unit circle? That would be seemingly a bad situation. So we have basically in any interval that you take, there is an eigenvalue. That's seemingly a bad situation for this theorem, but really it isn't, because we can restrict the action of the operator to span of functions e to the I k theta for finite k, right? And that's that finite resolution that I spoke about at the beginning. And so the operator itself, in this particular case of the rotation, would actually only have a finite number of eigenvalues restricted to that subspace, and therefore the theorem is valid. Now, in principle, one can get all the eigenfunctions and eigenvalues you want using this methodology that is called the generalized Laplace analysis. In practice, you might encounter some problems, because at large T, if your eigenvalues have magnitude less than 1, then it involves multiplying a potentially very large number with a very small number, and that can cause instabilities. Now there are numerical methods to resolve these kinds of issues, but I will not discuss them further. So here is a nice little example. So if we consider the classical nonlinear van der Pol oscillator model, so we take x1 dot is x2 and x2 dot is minus x1. So this x2 and minus x1 would form a harmonic oscillator. But then we had mu x2. And so for positive mu, this would be some kind of a forcing that is dependent on position. And then we had minus x1 squared x2 times mu, which would be a nonlinear damping. It is well known that this combination of nonlinear damping and forcing makes the system have a limit cycle in 2D. So this is x1 and x2. So that's the limit cycle of van der Pol for mu is equal to 0.3. And that limit cycle has motion on it that is rotational motion with a frequency omega 0 is about 0.995. And so this frequency here turns out to be a candidate for the Koopman eigenvalue. Indeed, I omega 0 is, we talked about rotational processes, and we found out that the frequency of rotation leads to an eigenvalue that is I omega 0 in the introductory lecture. So that's the case for the van der Pol oscillator. There is an eigenvalue with that is related to the frequency that is plus minus I omega 0, a complex conjugate pair of eigenvalues. And therefore, according to the prescription above, if we formed, if we chose some function f and we formed the sum, so we did 1 over n sum, let me choose the same notation as here. So I'm denoting my function as h. The observable is h. So sum h of that I have obtained at some interval j. So j starting from the initial position x, k, and then multiplying with that e to the I omega 0 j delta t, that should produce an h star, and I'll label it as omega 0. It's really, according to my notation, it's really h star e to the I omega 0 t. So this would be a of t, right, in my previous notation. So that's the weight in this sum. So the idea is take the domain, put initial conditions on the domain. In this case, we had 80 by 80 grid of initial conditions. Form these sums, you get h star, and that h star, by the previous theorem, is an eigenfunction. Now, of course, the modulus of the eigenvalue here is 1, so no trouble, no issue with subtracting. But here is the plot of the level sets, and you're seeing basically also the in black here, you're seeing some level sets outlined for minus pi over 2, minus 3 pi over 4, and so on. It's kind of a classically computed by backwards integration method, the same. But you're seeing the level sets shaded are basically giving you a separation of the points on the limit cycle, right, by something that looks like a phase extended to the whole state space. So this is the level set. So this is the image of an eigenfunction of the Koopman operator associated with the van der Pol oscillator when we chose the weights to correspond to the eigenvalue I omega 0. Now, if we wanted to compute, there is another eigenvalue associated with the limit cycle, and that's the so-called Floquet exponent that tells us about the rate of convergence of trajectories to the limit cycle, because the way the dynamics of limit cycle goes is a second, is convergent to the limit cycle itself, both from the inside and from the outside. And so there is another eigenvalue, let's call it lambda, and that lambda is less than 0 and tells us something about the dissipation rate towards the attractor. And that eigenvalue lambda leads to an eigenfunction that we could obtain by Laplace analysis as well, but we would have to subtract the eigenfunction that we already got from I omega 0, because that one has magnitude 1 and lambda has magnitude in the complex plane less than 1. So that's all that we're going to say about the generalized Laplace analysis. And then next time we're going to talk, oh, I did forget to say that h of x1, x2 was just some arbitrary function x1 plus x2. One of the benefits of generalized Laplace analysis is that you don't have to be so careful about which observables you choose. You can just take the ones that are given if it's observational data, or you can construct one like we did here. Next time, we're going to talk about the methods that pertain to that actually rely on constructing the operator itself. While here, we didn't have to construct the operator in order to obtain the numerical results.